Okay, the last presentation was a bit interesting, and this will be very hard to understand, and so I don't know how much it will be relevant to some of you, but let's talk about it. So, oscilloscope. When you have different wave shapes, you can't measure it with just plain multimeter. You have to measure it in visual way with oscilloscope. And these are some waves that you're going to see on your scope when measuring. And this is very hard to measure with multimeter. And you see there's a bunch of stuff going on. There are some transients, unperfect waveforms, and two same waveforms shifted in time and by phase, and etc. And for all that stuff you need oscilloscope. Waveforms are very rarely sine wave or perfect square or perfect anything. Usually you get a bunch of deformations or noise or something not very ideal. This is not very ideal square wave, and this is one of the most prevalent reasons to use oscilloscopes to watch for very strange waves that are happening in electronics. There are two types of oscilloscopes, analog and digital. Digital, they are DPO, sampling, mixed domain. Most modern and most expensive digital oscilloscopes can show you both analog and both with digital waveforms and what's going. So it's more of analyzer than just a scope, but that's very advanced. We'll take a look at analog scope, and most of the functions are same for analog and digital. And what's good, we can take a look at virtual oscilloscope, and you can find it on that address. It's free. It's sort of a plug-in for your browser, and it represents some very real analog oscilloscope with regular controls. And I'll try to quickly just some of the most basic controls to allow you to play with this thing. So, you have to first power it on. That's a power button. On every oscilloscope you can change the intensity and focus of beam that is going on your display. Trace means that you can, because trace is always straight, you can change its angle if it's crooked. On some oscilloscopes you can find beam finder and scale illumination. Scale illumination is how is scale on your scale is that display here, how it's illuminated by backlight. Beam finder, if your beam is somewhere outside of your display, you can find it with this button. There's no that button in this virtual oscilloscope, but you can usually find it on some real scopes. This is a two-channel scope, so you can watch simultaneously two different waveforms. You have two BNC inputs, like in real one. That's where your probes will go in. There's a DC, AC, and ground switch. What that means? Depending on what you're going to measure, DC is for measuring DC voltages, AC for measuring AC voltages, and ground means finding a reference. If you ground your input, you can find where is zero level for your channel. And I'll show you why it's that important. In the middle, you get buttons for determining what kind of display you're going to get. If you press first button, channel 2, you'll get display of voltage that is connected to right channel, channel 2. If you switch it off, you'll get just a left channel. You can display both channels with dual, and you can display the sum of these two channels with add function. If you select both buttons, you'll get chopper mode when piece of one signal is displayed, then piece of other. Again, piece of one, piece of other. I'll show it to you that later. Most of the time you are measuring with AC. And when measuring with AC, you can also measure DC voltage applied to AC voltage. First, horizontal. But let's take a break here. First, I skipped part about theory, how this oscilloscope works. But what you have to know, the point on the display goes up and down with the change of, say, sine wave of the input. If you just apply sine wave to one input, what you're going to get? You're going to get a dot on the display that goes up and down depending on the value of the amplitude of that sine wave. You won't get a picture of sine wave. You just get a momentary value of amplitude that goes up and down. You need a voltage that will spread this change over your display. And it's called time base. So, this is the linear voltage generated by the oscilloscope itself, and it spreads this change of one dot from left to right side of the display. If you correctly set this linear changing voltage, you'll get a nice sine wave on your display. Maybe, okay. Time division, what's that for? Let's see. Here's the sine signal that we are measuring. And let's forget about controls. What we are seeing is sine wave on your display. And how to determine what's the frequency and amplitude of this signal. As I said, if I don't have a time base, I won't get this sine wave. I'll get just one dot going up and down. If I get a right time base, I'll get this nice representation of sine wave. What's the frequency of this sine wave? Well, let's watch two dots when it starts to repeat. So you have 1, 2, 3, 4 squares between dots that represent full time period of this signal. If we go back here, time division determines how much this one square in horizontal is valued, and that's the speed of your time base. Here it's set at 2 milliseconds. Here is at 1, but for this wave it's 2 milliseconds. What that means? It means that your signal goes through 4 disk squares and each square is 2 milliseconds. So this signal needs 4 times 2, 8 milliseconds to do one full cycle. What's the frequency? Frequency is 1 divided by time, so it's 1 divided by 8 milliseconds. That's 1000 divided by 8, and that's how much? What's 1000 divided by 8? Why 125? So the frequency of this signal is 125 hertz. And that's what's determined by this control. You control the value of this horizontal scale. If you set it to 1 millisecond, the picture will stretch. The signal itself won't change, but you'll actually zoom the picture. So you can't change the signal with this oscilloscope. You can just change the way you look at the signal. You can zoom in or zoom out. There's a calibration also. For calibration, that means that you can have some sort of zoom on some specific part of signal, but if you turn it, you'll then lose your calibration. It won't be any more 1 millisecond per square. X position, that means you can move this signal left and right. So you can say move these peaks on some places that you can easily determine when it starts and when it finishes. So X position moves left and right the whole signal. Magnification 10 times will put picture 10 times larger on your display, meaning that some little changes in signal can be easily seen. So we determined the frequency of this signal. What's the amplitude? Again, we count number of squares, 1, 2, 3, 4, 5, 6 squares for peak-to-peak voltage. Amplitude is half of that, so amplitude is 3 squares. And at this control volts div, it means how many volts you get per one divide. You get half volt for 1 square. So amplitude is 3 times that. Amplitude is 1.5 volts of this. If I change it to 1 volt, the picture will be squashed 2 times. It will still be 1.5 volts amplitude, but you'll actually do a zoom out. You get 2 set of controls for this, meaning that you can represent 2 separate signals with single time base. You'll see that. So this is the waveform we're talking about. I already explained it to you how we determine frequency and amplitude. This is where we control for both signals volts div. Also, you can uncalibrated to watch some tiny portions of it. Y position means that you can move the position of a signal up and down. And if you if you're looking at two signals in the same time, you'll move one signal up, the other down, so you can see both in the same time. Invert means that you can invert the input signal. And this is it. I'm looking at two signals at the same time. Signals have the same frequency, but the amplitude is different. Why is that? Both controls here are set at 1 volt per division, and you see that upper has 1, 2, 3 squares, that's half. First one is 1.5 volts in amplitude. Second one is 1, 2, 3, 4, 4.4. So second one has 2.1 volts amplitude. With this Y position for left and right channels, I can determine and move positions of these two signals so I can watch them in the same time. Triggering. Triggering is something very tricky to explain, but actually to have a steady picture on the display, you have to make a synchronizing signal with the input signal. If there's no synchronization between input signal and oscilloscope itself, the picture will travel from left to right. And there are many ways to control that trigger. Most of the time you will control this trigger level, and you can set it to work AT automatically or normal. Normal means you control it with manually. You can change it until the picture is steadied. Here you control types of synchronization. If you don't know what's that for, don't bother. You can synchronize it to some standard TV voltages. That's not very interesting, but you can synchronize it to AC voltage, DC voltage, high and low filtered voltages, and to AC mains at the input, and also you can invert the triggering signal. You can delay that triggering signal, so the triggering is a bit late than the signal itself. And you have also the external input for triggering if you want to signal be synchronized to some other external voltage. Anyway, you most of the time use just this level. When you're measuring some signal, like this one, if you want it to be steady on the display, just move a trigger, and what trigger does is changes the level up and down, and when it finds something to be triggered, like this value of sine wave, it will synchronize and put a steady picture on it. Calibration. If you have played with this red meters, potential meters, you uncalibrated the oscilloscope. To calibrate it again, you connect your probe to 0.5 or 0.2 or 2 volts square, and you can then scale it back to the calibration. You know that this output is 2 volts square wave, and you set your controls so it can represent just that wave. XY mode. It's a bit hard to explain, but in this mode you're actually representing two signals and how they depend between each other. There's no time on X scale, rather one on Y scale is one input, on X scale is other input. So you won't get this type of representation. Why? Because on the X scale is time. If I now put this second waveform on the X scale, I'll get a circle. What that means? It's Lissajous figures, and they represent phase and frequency between two signals. Circle means that these two signals are the same frequency, and if it's flat, it means they're in perfect synchronization, meaning there's no time delay, time shift between these two. Now, if I look at these two signals, this signal, upper, is actually the same signal as upper signal in here, but what's changed? Changed is volts div. It used to be 0.5, now it's 1, and I changed from 2 to 1 millisecond time division or time scale. So now I get stretching of the signal, and the other signal now is different frequency. If you get different frequency signals in XY mode, you get something like this. And what it shows that if you look outside dots, you had 3 dots in Y scale and 2 dots in X scale. That means that frequencies of those two signals are 2 to 3 scale ratio. And there's a short preview of these things. So you get perfect circle for 1 to 1 scale ratio. If you get this type of figures in XY mode for 1 to 2, 1 to 3, 1 to 4 frequency ratios. Probes that you're going to use for measuring are something like this. They usually have switches 1, 10, and 100, meaning that they can scale down the input voltage 1, 10, or 100 times. And it's useful for measuring high voltages. So if you're measuring, say, 1000 volts, this high voltage probe will scale it down to just 0 to 10 volts. Because oscilloscopes have a very limited input range, up to 5 or 10 volts. Those are passive probes. Active probes can amplify small signals 10 or 100 times. Differential probes actually measure signal between 2 points, not between ground and output. This clip is where the grounding goes on your circuit, and you touch this point to the point where you're going to make a measure. There's also a small trimmer on the probe. Usually you don't have to mess with it, but if you're watching some square signals, you'll see that if it's not trimmed right, you will get not perfect square, rather some filtered square, so you have to set it to get the best response for your measurement. This is very complicated scheme, how this thing should be working. What you have to see is that this is that time base, linear voltage that is generated that puts that dot that makes sine wave from left to right on your display, and this is the input. This is the switch that determines what you're going to measure, AC or DC voltages. This is why it's important to have oscilloscope. This very ugly picture is how AC mains affect audio signal. You have to have, you expect to have some perfect high frequency audio up to 20 kilohertz, but that's this tiny sine wave. These big sine waves are just a hum of 50 hertz or 60 hertz mains. Also, in this example, you don't get perfect sine wave. You get it modulated by some low frequency signal. High frequency signal is hidden in this trace. You can't see it, but you expect to be flat. Actually, it's amplitude modulated by some low frequency signal, and that's very hard to determine without oscilloscope. This is magnification of that 5 volt USB voltage. You expect to have flat line of 5 volts. Well, it's not flat. It's fluctuating in time, but this fluctuation is several microvolts or millivolts, and also you have some high frequency superimposed on it, and that high frequency comes from switching of internal electronics in power supply of your computer. So it's not perfect 5 volts and it's not flat. There's a bunch of stuff going on in there. Digital to analog converters are considered perfect. Well, they are not. This one should produce perfect sine wave, and it's not producing perfect sine wave. Actually, it has some bad filtration to it, and it's just a rather harsh approximation of sine wave. When looking at square waves, you see that there's some ringing at the beginning and ending of transition at square waves, and sometimes these ringing oscillations can cause very bad stuff to your electronics. And this is typical for audio signals. You want perfect sine wave on your output, but you get some clipping, unwanted clipping of part of your sine wave, and that's not good. So this is the input, and the output is just clipped from the upper side, and on this example on the right, clipping is both up and down, and that's very bad. You see it's speaker out. You want perfect sine wave, and for some reason, probably because the power amplifier is at its maximum output, it's getting some clipping. And also you get some transients. You can look at signals, how some circuits respond to some input signals, and how fast they change their output state. And that's it for today. Thank you.